The last paper in this session is event-based visual-inertial velometer.
Hi everyone, my name is Zhou, and I'm going to present our work, Event-Based Visual-Inertial Velometer, a joint research project from Hong Kong UST and Hunan University. Vision-based state estimation, also known as visual odometry or SLAM, is a fundamental problem for mobile robots. However, its applicability degenerates in high-speed scenarios due to the limited sensing capability of standard cameras. This challenge poses inevitable demands for advanced sensing principles that can perceive the scene dynamics effectively, and also for compatible algorithms and software. Neuromorphic event-based cameras are biologically inspired visual sensors with asynchronous pixels and extremely high temporal resolution. And such favorable properties make them an excellent choice for solving state estimation tasks under aggressive ego motion. Nevertheless, failures of camera pose tracking are frequently witnessed in state-of-the-art event-based visual odometry systems when the local map cannot be updated in time. So to resolve this issue, prior works resort to visual inertial fusion or feature-based method. But one of the biggest roadblocks in this specific area is the absence of efficient and robust methods for data association without imposing any assumption on the environment. However, this problem seems unlikely to be addressed as in standard vision due to the motion-dependent observability of event data. And all these issues drive us to think about the following question. Is there a more rational design for an event-based visual inertial system that is more consistent with the differential working principle of event cameras? And to answer it, we propose a novel design of state estimator, which exploits the differential working principle of event cameras, and it recovers the first-order kinematics, namely the instantaneous linear velocity, by fusing events and the inertial measurements. So our method goes like this. Giving us input the raw events from a stereo event camera and the measurements from an IMU, the goal is to recover the instantaneous linear velocity in metric scale. And the front end computes the normal flow and the depth information respectively from the input events. And to this end, we provide a rigorous derivation for computing the normal flow from the spatial and temporal profile of event data. And as for the depth estimation, we simply apply a static stereo matching method. Our backend considers the synchronous property and high streaming rate of event cameras. Yeah, so basically we just proposed a continuous time pipeline which can handle the asynchronous event data and also can establish the data association with temporally non-aligned measurements from the accelerometer. And specifically, the objective of this task is to fit a cubic B-spline in the velocity domain that simultaneously satisfies the following two criteria. The first one is that the predicted normal flow must be maximally consistent with the normal flow observation. And the second one is that the first order derivative of such a B-spline must maximally comply with the acceleration measurements. So to evaluate our method, we use an event camera simulator to generate sequences which feature the aggressive maneuvers of a drone. Basically, two synthetic scenes are generated, including a circular corridor, as you will see, in which the drone undergoes a high-speed detour, and the second one features a drone traveling through randomly distributed boxes. And we compare our method against several alternative solutions that can determine the linear velocity, and the results show that our method outperforms others in terms of both absolute and relative velocity error. Besides, we also perform evaluation using some self-collected real data, and as you can see in this video, the accurate linear velocity recovered by our method leads to better trajectories in terms of a global consistency, indicating that our method is a better solution to the problem of data reckoning. So that's pretty much about my talk, and we hope that our design can inspire future research in this specific area. So if you feel interested, please stop by our poster. Thank you.
We have time for one quick question. Okay, maybe I can ask a question if there's no audience question. So what is the limitation of this work?
So the limitation, as far as I see, there are basically two of them. The first one is that the measurements cannot go beyond the measurement limits of the IMU. So if it fails, okay, the system definitely failed. And also the performance of our system is quite relying on the quality of the normal flow, which is a visual input. So we do not explicitly explain how much texture must exist in the environment, but vision-based method, we must have some textures which can induce the brightness changes somehow can be used by our method. Yes.
Great, thank you.